In this video, I will share the behavior of an electric dipole when it is held in some external electric field. For this purpose, let me suppose a uniform electric field produced by two equally and oppositely charged plates. One is positively charged and the other plate is negatively charged. Due to these parallel plates, an electric field is developed in the direction from positive plate towards negative plate. Now let me place an electric dipole having charge minus q and plus q at points A and B. So this is an electric dipole. Suppose O is center of the dipole and we are to observe the behavior of the dipole when electric field is switched on. Due to this positive charge plate, this negative pole of the dipole will be attracted towards this plate and this positive pole will be attracted towards negative plate. As a result, two parallel forces act on the electric dipole. Let's calculate the magnitude of these forces. Let me call this force as F1 vector and this force as F2 vector. Magnitude of F1 is equal to Q into E because electric field is defined as force divided by charge. Similarly, magnitude of force on charge plus Q will also be same. So magnitude of both the forces is same. Directions are anti-parallel to each other. We call it a couple of equal and anti-parallel forces acts on the dipole. And due to this couple of forces, a torque will be developed on the electric dipole. How to calculate this torque? Torque of a couple is defined as the product of either force and arm of couple of forces. So either force, both are same. It will be Q into E. And what is meant by arm of couple? Arm of couple can be calculated as by drawing a triangle, right angle triangle like this. Let me call this perpendicular a point C. So this distance from A to C, arm of couple means distance between minimum distance between two anti-parallel forces. This minimum distance is called arm of the couple. I have written it as distance AC. It is to be calculated. Let us suppose electric field again passing through this. Suppose this angle is theta. If this angle is theta, this will also be theta, alternate angles. Now we have to find the value of AC. From triangle ABC, I can write sine theta equal to perpendicular over hypotenuse. With respect to this angle theta, perpendicular is AC and hypotenuse is AB. After cross multiplying, I can find AC is equal to AB sine theta. Now what is AB? AB is length of the dipole. Let me suppose length of the dipole is L. So AC will come out to be L sine theta. Now I will put this value of AC in equation for torque. So putting the value of AC, the torque can be written as tau is equal to QE multiplied with L sine theta. I can write tau equal to QL multiplied with E multiplied with sine theta. Q into L is nothing but electric dipole moment. I can replace it by P, that is PE sine theta. So this is the expression for torque that will act on the dipole when it is held in external electric field of magnitude E at an angle of theta. In vector form, this torque can be expressed as P vector cross E vector. The direction of torque can be found by using right hand thumb rule for cross product of two vectors. Due to this torque acting on the dipole will tend to rotate in clockwise direction. Due to this couple of forces, this torque is created, and this torque helps the dipole to rotate in clockwise direction. Now let us suppose I rotate the dipole in direction opposite to its tendency. Tendency is to rotate along clockwise direction. I want to rotate in anti-clockwise direction. So what will happen? I will have to do some work against the torque. So small amount of work done, small amount of work done to rotate dipole through small angle, let me suppose d theta in anti-clockwise direction. Anti-clockwise direction. How much amount of work is required to be done? That can be calculated as dW equal to torque multiplied with angular displacement. So I can put value of tau. It will give you P E sine theta d theta. So total work done can be calculated by integrating it. When I integrate both sides, I can write PE integration sine theta d theta. This gives answer for W is equal to PE cos theta in magnitude. This work done in rotating the dipole through angle theta in a direction opposite to its tendency. The tendency is to rotate in clockwise direction. I am rotating against this tendency. So much work will be done on the dipole. This work done on the dipole is stored in it as its potential energy. So potential energy of dipole can be written as Pe cos theta. So this is the expression for how much potential energy is stored in the dipole when it is rotated in an external active field in a direction opposite to its tendency or opposite to torque acting on the dipole. That's all.